Welcome back everyone, I hope you had a really nice holiday break. I hope you recharge because now we start with the Calculus 2 modulus. But before we start doing exercise, I have a little gift for all of you. So this is Pascal and he's gonna be my assistant for this semester. And it comes with a lovely cheat sheet with all the basic integrals you need to know by heart. I will not bother you by reading them out loud right now, but I have prepared a PDF file with all of them in my GitHub repository. The link is pinned in the comment down below, and you can download it, and you're gonna thank Pascal later for it, because you're gonna need it during the semester. Now, let's start with the T-substitution technique for solving simple integrals. Today, we're gonna talk about one of the most powerful integration tools, the substitution method, also called T-substitution. To understand it, we have to look back to differentiation. So I know it's one of the most hated rules, but the chain rule was also one of the most important, because it tells us that the derivative of the composite of a function is the derivative of the function outside, evaluated the function inside, times the derivative of the function which was inside. Now we can simply integrate both sides respect to x. So on the left-hand side, by the fundamental theorem of calculus, derivative in integral basically simplifies out, and we get f composed g plus a constant c. The right-hand side, it looks a bit messy, but we can look at it a little bit closer. Indeed, if we define a new variable, t equal to g of x, we can greatly simplify our integral. You can see that inside we have now f prime of t, and we are left with this term g prime times dx. What to do with that? Well, if we do the change of variable t equal to g of x, we have also computed its differential. What is the differential? Well, when you take this change of variable, you have to take the derivative respect to t on the left-hand side, times dt, which reminds us that we differentiate respect to t, and on the right-hand side instead, we take the derivative respect to x, so in this case g prime, times the dx, that reminds us that we differentiate respect to x. And now we have this equality dt equal g prime dx. We can substitute that, and just like that, a really complicated integral became something really easy. So now we can start doing exercise and gonna see how to use this idea in practice. The first integral that we're gonna see today is the integral of 1 over 1 plus x. First things first, let's try to identify the f and g in this case. So g will be the function g of x equal to 1 plus x. So you see the function g exactly in the denominator. Therefore, f of x has to be equal to 1 over x, so the reciprocal. And finally, we can easily check now that the derivative of g prime of x, is equal to 1. So we are perfectly ready to use the following t-substitution. So t equal to 1 plus x. So this is what we are going to do. Okay? Now, how do you substitute this variable inside this integral and be sure that you have done it right? So, first of all, we are going to differentiate both sides. And on the left-hand side, we are going to differentiate respect to t. And on the right-hand side, we are going to differentiate respect to x. In this way, we are going to get 1 times dt, and this dt reminds us that we differentiate respect to t, equal to the derivative of 1 is 0, the derivative of x is 1 respect to x, dx. And this equality is telling us that the dt is equal to the dx. Great. So this integral is actually equal to the integral now. Instead of 1 plus x, we put t, so this is going to be t. And instead of dx, the second equality tells us that we can rewrite dt. So this is dt. And now this is an easy integral to do. This is just the log of the absolute value of t plus a constant. And finally, we have just to remember that we substituted t equal to 1 plus x, so we have to go back to x. This is going to be the logarithm of the absolute value of 1 plus x plus a constant c. As a second exercise, we are going to do this integral x times 1 plus x squared to the power 7. It might look scary because we have this ginormous power 7, but actually we don't need to do any power law here. We don't have to expand this guy. We can do it directly without actually caring about it using t substitution. Indeed, in this case, what we really don't like is this 1 plus x squared, right? So this 1 plus x squared is not that nice. So let's try to get rid of it using a t sub. In particular, what I'm going to do, I'm going to put t equal to 1 plus x squared. To compute the substitution now, so to substitute t here, I need to compute the differential. So I differentiate from respect to t on the left-hand side, and I differentiate respect to x on the right-hand side. And I get that dt has to be equal to 2x dx. So here what I did, I took the derivative with respect to t of t. It's going to be 1 times dt. That reminds us that we differentiate respect to t. And on the right hand side, I do the same, but I have a dx because I differentiate respect to x. Great. So now I can actually substitute t in this expression, and you notice that the dx is basically there, right? Because I have x dx, which is still here. So if I bring these two on the other side, I have a nice expression of x dx in terms of the dt. So what I'm going to do, I'm going to do dt over 2 equal to x dx. And now you see that I have x dx here all together, and this is going to become my dt over 2. And 1 plus x squared is going to become my t. So it's going to be equal to the integral of t to the power 7 times dt over 2. And now this integral, I can do it. So this is going to be equal to t to the power 8 divided by 8 times 2, which is 16, plus a constant. And now I have to remember that for me t is equal to 1 plus x squared, which means that this guy is equal to 1 plus x squared to the power 8 divided by 16 plus a constant. For this exercise, we have a situation which is really similar to the one before. In this case, 1 plus x squared is in the denominator, and the x is still in the numerator. So what we can do? Well, we can try the same substitution as before. So we set t equal to 1 plus x squared. And again, we compute the differential. So differentiate respect to t on the left-hand side, and we get just dt equal to 2x dx. And again, you see that in the integral we have x in the x, so there is an extra 2, but as before we can just bring it on the other side, so we get that dt over 2 is equal to x dx. And now we can do the substitution, so this becomes equal to the integral of dt divided by t. And again, this is just the logarithm, so this is just going to be the log of the absolute value of t plus a constant. And finally, I just remember that the log of the absolute value of t is just the log of 1 plus x squared, because that's what t is equal to. So this is the log of the absolute value of 1 plus x squared plus c. And now to be extremely precise, 1 plus x squared is always going to be positive, which means I can rewrite this without the absolute value. This is the log of 1 plus x squared plus a constant. As tradition to this channel, the last integral has to be really, really complicated. But as always, this looks like a monster, but actually is not that bad. So let's look at it. First things first, you notice that here we have 1 plus x squared, and up here we have 2x, which is exactly the x derivative of the denominator. So second take. As tradition to this channel, the last integral has to be difficult, or at least has to look difficult, like this one. So let's have a look. Here we have 1 plus x squared inside the log, and here in the denominator. And here in the numerator we have 2x, which is exactly the derivative of 1 plus x squared. So a good first substitution can be to put t equal to 1 plus x squared again. And in this case, we will get the dt to be equal to 2x dx. Okay, this looks pretty good and promising. Indeed, we have the 2x dx above here in the numerator, and the denominator is just 1 plus x squared, which is going to become t, and the log also, the argument is 1 plus x squared. Okay, let's do the substitution. So we get that this integral is equal to the integral of the log of t divided by t times dt. And this is an integral that we cannot do directly, but we can use a substitution also in this case to solve it. Let's write it down here again. So this is the integral of the log of t divided by t in dt. And now let's notice that if I set u equal to the log of t, and I try to compute the differential in this case, on the left hand side I still get du, and this has to be equal now to the derivative of the log of t respect to t, and the derivative of the log of t is 1 over t dt. Wait a minute. So u is going to be my log, and then I have dt over t, which is exactly my du. So this substitution makes this integral really easy to do. Indeed, this is equal to the integral of u in du. And now we can easily do this integral. This is just u squared over 2 plus a constant. And now we have to remember first that u is equal to the log of t. So it's going to be equal to the log of t squared divided by 2 plus a constant. And then we have to remember that t is equal to 1 plus x squared. So this is going to be equal to the log of 1 plus x squared all squared divided by 2 plus a constant. So if there is one thing you take away from today, please let it be this formula. Because in general, if you have an integral of f of g times g prime of x in dx, you can solve it by substituting t equal to g of x, and you're gonna get just the integral of f of t in dt. Don't worry if this is a bit tricky at first, because spotting patterns like this takes time and practice. Download the cheat sheet, do exercise, and I will see you in the next video.